This presentation will look to explore and explain the effects of chronic hypertension on glomerular filtration. The presentation will do so first by exploring what chronic hypertension and glomerular filtration is. Subsequently, the presentation will explore how the two interlink and affect one another. Chronic hypertension is an increase in blood pressure maintained over a prolonged period of time. Blood pressure is the pressure the blood is placing on the walls of the arteries as it is being pumped through from the heart. Ventricular contractions ejects blood into the major arteries, resulting in flow from regions of high pressure to regions of lower pressure. As blood flows through smaller arteries and arterioles, then capillaries, followed by the venules and veins of the venous system. This blood pressure can be expressed in numeric form as two numbers. The top number is the maximum pressure your heart exerts while beating, known as systolic pressure, and the bottom number is the amount of pressure in your arteries between beats, known as diastolic pressure. Normal blood pressure is less than 120 over 80. Pre-hypertension is blood pressure between 120 over 80 and 139 over 89, and high blood pressure is 140 over 90 or higher, which may eventually cause health problems such as heart disease and renal disease. Cardiac output is a measurement of blood flow from the heart through the ventricles and is usually measured in liters per minute. Any factor that causes cardiac output to increase by elevating heart rate and/or stroke volume will elevate blood pressure and promote blood flow. Conversely, any factor that decreases cardiac output by decreasing heart rate and/or stroke volume will decrease arterial pressure and blood flow. These factors include parasympathetic stimulation, elevated or decreased potassium ion levels, decreased calcium levels, anoxia, and acidosis. Hypertension can have copious physiological effects on the human body. This leads to dangerous complications such as kidney damage, heart failure, artery damage, and even death if left untreated. Glomerular filtration is a process by which dissolved solutes such as urea, electrolytes, and metabolic waste in blood, more specifically the plasma portion of blood, are filtered by the kidneys and expelled via urine. The base filtration unit of the kidney is called the nephron, each of which contain microscopic filters called glomerulus, which are a bundle of specialized capillaries. Blood enters the glomerulus via afferent arterioles and exits via relatively constricted efferent arterioles. This difference in arteriole size creates hydrostatic pressure in the glomerulus, which facilitates diffusion of the solutes across the pores of the glomerular capillaries into the glomerular capsule, also known as a Bowman's capsule. The glomerular capillaries are fenestrated, which means they contain microscopic pores that allow them to act like a strainer, such that only solutes of a specific size can be removed by the kidneys. This unique feature of the glomerular capillaries makes them 100 to 400 times more permeable than capillaries in skeletal muscle. Once the filtrate is passed into the Bowman's capsule, it proceeds down the nephron tubule before eventually being expelled from the body via urine. The glomerular filtration rate, or GFR, is largely governed by the blood pressure as it enters the glomerulus. The kidneys can auto-regulate the rate of filtration by constricting the afferent arterioles to maintain constant pressure in the glomerulus. These functions allow the kidney to handle normal fluctuations in blood pressure that occur throughout the day. Typical GFR in healthy individuals is approximately 170 milliliters per minute up to the age of 40, which then proceeds to steadily decline beyond this age. The kidneys are built to handle daily fluctuations of blood pressure. They do this through stretching and tightening the capillaries to alter the amount of blood traveling through the filtration mechanisms, which allows them to change the rate of filtration to match the needs of the body. However, this ability cannot be maintained for extended periods of time. When the kidneys are faced with chronic hypertension, the constant pressure overpowers the kidney safety mechanisms and the glomerular filtration rate is forced upwards, which over time can damage the glomerular membrane by stretching and scarring the delicate tissue. This membrane separates the arterioles from the glomerular tubule, allowing for waste products and excess water to be turned into urine. Whilst keeping blood and protein in the venous system, if it is damaged, the nephron is unable to remove waste and extra fluid efficiently from the blood, and will also let proteins and blood cells to leak into the urine. This excess fluid that re-enters the venous system will result in a further rise in blood pressure, creating a dangerous positive feedback loop. One important blood protein which can be unintentionally filtered out of the venous system is albumin. Albumin's role within the body is to draw excess fluid from tissues into the bloodstream to be filtered by the kidneys. However, with a lower concentration of albumin, the blood absorbs waste at a slower rate, which can result in the swelling of the face, hands, feet, or ankles. Some long-term complications of chronic renal disease can include anemia, cardiovascular disease, and dyslipidemia. However, these conditions are mostly preventable through controlling your blood pressure by lowering alcohol intake, smoking less, controlling your diet, lowering sodium intake, and exercising regularly. Firstly, this presentation explored what chronic hypertension and glomerular filtration is. The effects of the two on each other was then explored. This presentation concludes that chronic hypertension has negative effects on glomerular filtration. If left untreated, long-term issues such as kidney disease may arise. Due to its significant effects on glomerular filtration, it is important that chronic hypertension is not left untreated.